And we'll conclude our presentation day with a nice lady with the last presentation of today, Petra Hlavinová. Hello, hello. So Petra, well, we have the last presentation, automated data preparation and sensitivity analysis of energy consumption. Hopefully you'll enjoy the presentation, the last presentation of today.
During this last presentation, I would like to have a look at our approach. How do we process data in the context of analyzing energy consumption? So most of technical projects don't start with modeling. Usually it starts with struggle with the data. In industry, very often the data is not synchronized, not clear, not complete, and we don't know what is what. So then the analysis is also unclear. You can't really replicate it, and very often it also requires manual input, and this is what we want to address. Our objective is to create a system which, regardless of the input, we will have a structured output, and it will not require manual interventions. And in my presentation, we will speak about these 4 blocks. So this is data loading, data validation, data transformation, and sensitivity analysis. I want to spend most time on it. So let's start with the reality of industrial data. Very often the data is not heterogeneous, it's not full, not complete, or missing. And this is what we do. Those 4 steps we perform in an automated way, and we want to have a unified structure at the end which will explain what kind of data do we have, what are the problems, and we will be able to address the problems. At the beginning, we have data loading, and we can have a look. It can be simple. It may sound simple, but it's not always true, because the problem here is very often the data can be in a different format, different columns. Sometimes we don't know what the columns mean. Some might be missing. And this is why we are using 2 approaches, and one is this kind of deterministic processing that we are trying to use. So we can have Excel, CSV, PDF, and doc documents, and with a timestamp. Timestamp is very important, and we match it with our measured information. So we also have a large language model which help us identifying the roles, the columns, and the units. If we use this approach, we will come to the fact that our data in different formats, we will kind of unify it, and it will be a one single output with the same structure, and then we are able to work with it. Then comes data validation, which means that some of the data, and we have already seen the data, and some data can be slightly problematic, and these problems for us form a barrier, and we need to address it. In these 2 columns, you see what kind of validation checks we do, because the model cannot contain all the types of inputs. The data needs to make sense. It has to be meaningful. So on the left part, you have the classic checks. So basically, you exclude outliers, you kind of fill in the missing values, and then we have the detection of anomalies. So it's not only the technical problems or errors, but we also detect what are the relationships, are there any irregularities, and so on. And the output is that for those data we can record, we flag them, and we can identify problems. Apart from that, we also have something called agent report. And in this, not only do we acquire a chart of the errors, but this agent report also helps us to summarize it and to have it a human readable summary, explaining what kind of issues, problems, what could be the root causes. For example, when there is no measurement, and there is also a suggestion for threshold adjustments. Next step is transformation. we detected all the problems, and after that we need to address them in a way. This is a standard data set input, so there are gaps, there are peaks or spikes, and we have identified them and we need to address them. And this is how we do it. We do it in 2 layers. The first layer is time series normalization. We are trying to align the time steps. We are trying to remove the gaps. We want to have aligned timestamps, basically. The second step is signal correction, and we do interpolation or smoothing, and this is how we deal with the spikes. So this was the data preparation part. Now let's look at the relations between the data. I divided this part into 3 parts. So we have automatic labeling. Here we look at the hierarchy of the devices that we have. Then we have time alignment, where we deal with kind of temporal inconsistency, and then feature preparation. This is something like a preparation into the model-ready inputs. Let me start with automatic labeling. Our objective is that we have some energy signals and we want to have a hierarchy. So, for example, this device is hierarchically under a different device. And so this is how we approach it. First, we detect the candidates. We look for numeric signals that could have like energy, like naming. So then we have a quality filter. And we also check whether we do have a significant number of data in the given column. So, for example, if we have 5 lines, it doesn't make sense to enter it into this hierarchy because it would not be trustworthy. Then we look for the root, which will be the top of our hierarchy. So this is the device which has of the biggest volume or biggest energy. Then we create pairs. It will be like a parent and child system. So the parent must be or mustn't be smaller than the child. So we are summing and we are also making an average. And once we pair it up, then we validate whether these pairs make sense or are meaningful and are trustworthy. I use 3 different metrics to do so. Not all of them have the same coefficient in my scoring. The most important is the constraint check, which is looking at the fact that the child value should not be greater than the parent energy. So we get something like a violation rate telling us in what percentage the child was greater than the parent. Of course, it shouldn't happen. Then it is spike alignment, where we observe that in case there was a sudden change with our child, then it is probable that also the parent should change. And if we look at the spike, we can get something like a spike rate. And the third matrix is the correlation, and we get to a score. And based on this score, we pick the best ones for our hierarchy. Next part is time alignment. Very often it happens that the data is not synchronized. So, for example, this can happen, which is an ideal example that our data is kind of dosed, or you see the energy in time and process, and the red one shows the production or energy consumption and the production. So, for example, 100 products were not produced in 1 minute, but it took the whole time during the whole process. But this is how we enter the data, and we use interpolation to kind of go back in time. So, based on the energy. And this is how it is then aligned on the same line with the energy. What also happens is that one can lead to the other, to the changes of the other, but never at the same time of the signal. So we can also have a look at the last 24 hours past and the new ones, and we look at the correlations between the two signals. And we look at the correlation, but not only. We also look at events. So when there was a significant change of the flow, or there was, for example, a spike. And I'm also using a filter to do so. And then we are not using data which are not kind of suspicious, but then there is also fast screening, not to compare everything because that would be too exhausting. And we look at the biggest correlations, and then we also create pairs. What do we observe in these pairs is that in the most expected time, the result of the correlation, we look at the time window and then we observe it. And then again, we see in case of a spike, in one, there should be also a spike in the other. And we are still observing and looking at the correlations, and the result can be, we detect pairs. We don't check it locally, but overall. And we see it's not every alignment, but it has to be a consistent match between the events. And the last part is feature preparation. So looking for appropriate inputs for the model. And as has been mentioned, at the beginning, we look at the correlation. And this is like the first insight into the relations between the data. But it's not all we can do with it. I have decided to go on with a score, and during this scoring we look not only at the correlation but also whether are there any missing data. Again, in the model we don't want to have data which is missing or quantities which have missing data. Then we also look at the penalties, and we look at some constants, what are the numbers or quantities, and we come up with a score. Once we evaluate it, we split it into 3 groups, and some are interesting candidates for us, or then they didn't score too high, but they are still meaningful or make sense. And the last one is the layer that we don't consider, so it's a drop. And basically, this is all from my presentation. I would like to mention that this approach allows us to come from raw data to trustworthy signals, and it can lead to explainable insights at the same time. Thank you. And okay. Yeah, you were quite fast, luckily, so we thought we don't have any time left for questions, but we still have a few moments. Either we can do it via Slido, or let's have a few moments. Did you enjoy the presentation? How do you feel? I remember you from Trnava. You were a guest back then at the Trnava conference, but now you were a presenter. And now let's have a look whether the guests also have some questions for you. Let's have a few more seconds, whether some questions will appear. In case not, nobody wants to ask anything. Oh yeah, we do have a question. Okay, let's use the mic. Once you process the data from the raw data, how do you know that you will not catch the data that Tomáš Karasek will then exclude or not be able. So you have some different variables or values, and Tomáš Karasek is looking for some values. How can you set up that you don't remove data that Tomáš Karasek would need later on? Okay, so as for the values, I mean, for example, it can be wrong measuring, or, I mean, we are trying to exclude data that would not be good for measuring. Of course, it can happen that we remove something that might be important. Okay, what we do something like a profile processing, and of course it depends on the input signals and what we do process. Of course, some signals, I mean sometimes some things cannot happen on the measuring device. So some of the validation processes have respect parameters, and this is like profiling. Okay, I have a measuring device or meter device. I have the reference data, different settings. So we do have some settings for this kind of devices. So we are aware of the fact that we don't want to harm the data, but we are looking for a meaningful way how to pre-process the signals. We look at the condition, at the status, and then we look whether whether there is a regular occurrence or something. Yes, I understand your considerations, but the thing is, how do I set, and how it's not an easy process, the settings. I mean, there is really big options when you work with the settings, and this is what AI can help you. It's like a pre-selection of the profile settings of the validation. Thank you for clarification. And any other questions? Any questions in Slido? Nothing? Thank you, Petra. So one big applause for Petra Hlavinová. She was the last presenter.